Hi everybody, my name is Enrique and I'm a PhD student at Columbia University. Today I want to talk to you about graph simulation using maximum entropy distributions. This is joint work with my advisor, Paul Glasserman. So our problem is the following. We're interested in sampling uniformly from certain sets subject to linear constraints. The sets can be discrete or continuous, but for this talk and to make things simple, we're only going to focus on the discrete case. And as an important particular case, we have the problem of sampling bipartite graphs with given degree sequences. So this is the example that I want you to keep in mind throughout the talk. So the setting of our problem is the following. We start with a bounded set S of this form in n dimensions. And we have a constraint mapping H, which is a linear mapping. So it's given by a matrix A and a vector B. And this is a very important definition. The target set, we define it as the intersection of our set S with the linear mapping H. And we're going to assume that this target set is non-empty. So here I have an example on the right. So this is the way S would look in 2 dimensions. And then we add a linear constraint, and the intersection is the set we're interested in sampling from. So these 3 dots would be the target set. And when I talk about the binary case, I'm talking about this particular case when the S can only go from 0 to 1. And this is important because the graph case is particularly an example of the binary case. So let me talk briefly about the problem of sampling bipartite graphs using given degree constraints. So as you know, in a bipartite graph you have 2 classes of nodes, and the edges can only go from one class to the other one. So with our notation, the set S, which is a binary case, represents all of the possible bipartite graphs. And here n is just the number of possible edges, which in this case we would have 3 times 3 equal 9. So our variables x, the x variables, the xij, it just represents the presence or absence of an edge. So if xij is 1, it means that the edge is present, and if xij is 0, it means that the edge is absent. And now when we talk about imposing linear constraints on this problem, we mean that we're imposing a constraint on the degrees of the nodes. So for instance here, we have these graphs, and we add a constraint on the degrees. So we're imposing these degrees on the nodes, and then we just want to sample from all the possible bipartite graphs that satisfy the degree sequences. So for example, with this degree sequence, here we have 2 possible graphs that satisfy the degree constraint. So our goal is to sample uniformly from our target set S of H. So what we're going to do first is we're going to study 2 candidate distributions, which we will call the maximum entropy distribution and the maximum probability distributions. So we're going to define them, and they're going to show an important relation between the 2 of them. And then later, we're going to propose a sequential algorithm using the first one, the maximum entropy distribution, to increase the probability of simulating a point in S of H. The problem of simulating graphs with degree sequences is not new, and there are several methods in the literature to do so. So for instance, you have the pairing model, switching models using MCMC, and other methods using sequential importance sampling. So what I would like to say here is that all of the methods have their advantages and disadvantages, and there is not a clear dominant method. And there's also important theoretical work on maximum entropy with linear constraints, and also a connection between maximum entropy and uniform sampling. And so we were inspired by these 2 works. And I'm going to leave more details on the literature at the end of the slides if you're interested. We now define the entropy function, and we're going to use the classical definition. So given a distribution P on S with a density or mass function P, the entropy is defined as this sum or this expected value. And so here we have the first connection between entropy and uniformity. Why is that? Because if you take QU to be the uniform distribution on S, you can see that the entropy of the uniform distribution dominates the entropy of any other distribution P. So this means that the closer you get to the uniform distribution, you increase the entropy. But of course here we don't have any restrictions, and we have seen that in our setting we have linear restrictions. So we're going to impose those next. So now we define our maximum entropy problem. So if you recall, we're interested in sampling points that satisfy the linear constraint hx equal to 0. But since now we're talking about distributions, what we're going to do is we're going to impose those restrictions but in expectation. So we define C to be the set of distributions P on S that satisfy the linear constraint in expectation. And we consider the following problem. We're going to maximize the entropy subject to P satisfying the linear constraint in expectation. And so this is a very well studied problem, and we have the first result. And the problem is the result is that this problem has a unique solution, P star. So P star is what we call the maximum entropy distribution, and this is going to be our first candidate distribution to sample from the target set S of H. And we're going to denote Y star as the mean of P star. So now what I want to do is to be able to characterize P star. Consider the following exponential family, P of eta. So the parameter eta is any vector in Rn, and the density P eta is defined as the following. Well, it's exponential, so of course we have this exponential form, and in the exponent we have eta transpose x. And you can see easily that this distribution has independent marginals, and the marginals are also exponential. And here g of eta and gi of eta I, these are only constants that help normalize the density. And I wanted to draw attention to the particular case eta equals 0, because see here, if you put a 0 here, all of this will become constant. And so that means that when you set eta equals 0, you recover the uniform distribution QU. Our next result says that P star is a member of the exponential family P of eta. So that means that to find P star, we only need to find its parameter, eta star. And this has a very particular shape, and it's of the form lambda star transpose A. So it depends on the constraint matrix A. And the second part of the proposition just gives us the maximum entropy, which is given by this form that depends on lambda, B, and also the matrix A. And this value will show up again later in the talk. So here I just want to say that this means that to find P star, we only need to find the lambda star that satisfies these constraints. And so this amounts to just solving a nonlinear system of equations, which numerically can be done pretty efficiently. So now take X in the target set, and then we're going to evaluate it in the density of the maximum entropy distribution. So if we use the form of the exponential family, we get this. And now we see that since X is in the target set, we know that it satisfies the linear constraints. So AX equals B. And you can see that this is a constant, it doesn't depend on X. So what this means is that the maximum entropy distribution is a constant on the target set. So this does not mean that it is uniform on the whole set S, but if you restrict to the case where the point is in the target set, we have uniformity. And so this leads to the following very simple acceptance rejection method for sampling from S of H, which is our initial goal. So the algorithm is as follows. You first generate a sample X using the maximum entropy distribution. If it's in S of H, then you're done, and then you return X. But if it is not, you reject the X and go back to step 1. So this is simple, but you will see that it's not efficient and practical, because this probability in real cases will be extremely small. So you will end up rejecting most of your samples. So later we're going to propose a sequential algorithm that's going to fix this issue. So now let's talk about our second candidate distribution. So this is using a different approach. We use the same exponential family, but now we say, okay, since we're interested in sampling from S of H, what we can do is the following. We take the minimum of the probability across all of S of H, And this is a function that depends only on the natural parameter eta. And then we ask ourselves, what is the eta that maximizes this minimum probability? And that is exactly our max-min probability problem. Now, if this problem has a solution, and if that solution is attained at some eta hat, then we will call P of eta hat the max-min probability distribution. Now, this problem is not as simple as in general as the other maximum entropy problem. But we'll see how we can link both of them. So this is the main result of the talk. It turns out that in some cases, the maximum entropy distribution and the max-min probability distribution are actually the same. And this happens if and only if the mean of the maximum entropy distribution is in this set, the convex hull of the target set. And you might ask, how do we get this? Well, here is some intuition. If you recall, the maximum entropy distribution assigns constant density to the target set. And that constant density or constant probability is this value, exponential of minus the entropy. So this implies that if you take the minimum probability across the target set, since they are all the same, well, you have that the minimum probability is this value. So here you can see that we have on our two objective functions evaluated at the same distribution. So this suggests a connection between problems 1 and problem 2. So we're interested in knowing when the condition of the theorem is satisfied. Well, it turns out that this condition fails often, and it fails in the discrete case, which is the case we're studying right now. So what we concluded is for it to hold, we need to add some additional structure on the constraint function h, and in particular, structure on the matrix A. So a sufficient condition is for A to be totally unimodular. And the definition is here, and a matrix is totally unimodular if the determinant of all of its square submatrices is equal to 0, 1, or minus 1. So we have the corollary of our theorem, and it says exactly what I was saying before, that if A is TUM, and also we have to impose that B is an integer vector, then the condition of the theorem is satisfied, and it means that the maximum entropy distribution is the same as the max-min probability problem. And this condition, the TUM condition, might seem too stringent at first, but then it turns out that in the bipartite graph case, which is the example that we always have in mind, this condition is satisfied. And so that it means that in the graph case, both distributions, the maximum entropy distribution and the max-min probability distributions, are the same. So now let's talk about the sequential simulation part. If you recall a couple slides back, I talked about this very simple but very inefficient acceptance rejection algorithm. So as I was saying, the acceptance probability will be very small, and so we cannot use this algorithm. So what we did is we proposed a sequential algorithm that will use the maximum entropy distribution to increase the probability of reaching the target set. And the algorithm is as follows. Here I'm just going to consider the binary case just to make this simpler, but the algorithm for the discrete case is very similar. So the algorithm works as follows. You start with a problem of size n, and you're given a matrix A and a vector B, and the first thing that you do is you solve the maximum entropy problem to compute P star. And once that you have that, instead of sampling all of the entries at the same time, you're just going to pick one entry. Let's say that you pick x1, and you're going to simulate x1 using the marginal distribution. And in this case, since we're in the binary case, x1 can be 0 or 1. And then what you're going to do is you're going to update the problem. So first, since you have already fixed an entry, you reduce the size of the problem from n to n minus 1. And the constraints are updated as follows. So basically from A, you take out the column that corresponds to the entry. So in this case, we take out the first column. And you update the vector B as follows. And then you continue. You continue all the way till n equals 0. And then you'll have a point x, and that is the point that you return. So I have included an illustration of this algorithm for the graph case in the appendix. So if you're interested, you can look at it on the slides. So now, here I just want to briefly mention some of the properties of the sequential algorithm. So the first property that we're able to show, well, is that this algorithm always terminates, and that the point that it outputs is in the target set. So that's reassuring, since otherwise this algorithm would not be worth anything. We can also show that this algorithm can reach all of the target space. And what that means is that if you define Px to be the probability of sampling a certain point with the sequential algorithm, it turns out that that probability will be positive for all the points in the target set. And not only that, but those probabilities are bounded away from 0 by this constant. And if you recall, this quantity we have seen before, and that is the max-min probability. So now the sequential algorithm looks great, since we can now always sample from S of h, but there is a cost to pay. And the cost is that we're losing uniformity. So the points that are sampled using the sequential algorithm will not be, in general, uniform on the target set. However, if we're interested in estimating quantities using the uniform distribution, we can always correct using importance sampling. So here I'm not going to give too much detail, but the point is that, yeah, we can weight our quantities by the importance sampling weights. And the importance sampling weights here are given by this quantity. So this is a cardinality of the target set, and it's unknown generally. So actually this estimator, we won't be able to compute it in practice. But what we can do is a small trick, and that is to just standardize by the sum of the importance sampling weights. And this will cancel this unknown quantity. And then this is an estimator that is biased, but consistent as the sample grows to infinity. And this is something that we can compute in practice. The last point that I would like to make is that the order in which the sequential algorithm selects the entries affects the distribution of the importance sampling weights. And this is important because when you're using importance sampling, you want the distribution to be as uniform as possible, meaning that you don't want large outliers, because that could jeopardize the quality of the estimation. So what we did is to consider different possible order rules, and then we just compare them to see which one gives the best results. And so here are the 4 rules that we follow. The first one is just you just visit the entries in order, so 1 to n. The second one is just at each step you select from the remaining entries, you just pick one at random. And then the last 2 are the most interesting ones because they are adaptive orders, meaning that at each step you use the information given from the maximum entropy distribution to pick the one that you will follow. And the definition is in the appendix, so if you're interested you can look at them. And just I want to say that empirically the most uniform adaptive order is the one that gives the best results. And then I'm going to show you like a quick example. So here is an example that we use from a degree sequence that we extracted from the Chesapeake Bay graph. And yeah, this graph is more information on this graph is in the appendix if you're interested. The idea is that we extracted the sequence and then we simulated 5,000 other graphs using our sequential algorithm that, all these graphs have the same degree sequence as the original Chesapeake graph. And then we did that for all of the 4 orders, and we compared the results. We compared the histogram of the importance sampling weights. And yeah, here, as you can see, the most uniform order is the one that gives a more bell-shaped distribution on the importance sampling weights. Clearly, the random order and the most singular ones, well, the distributions are more skewed to the right, meaning that you have very large weights. And that's something you would like to avoid when using importance sampling. Yeah, so to conclude, some points. The first one is that when you want to sample from the target set, you can consider 2 candidate distributions, the maximum entropy and the max-min probability distributions. It turns out that in some cases, and in particular when you're talking about simulating graphs, these 2 distributions are actually the same, so it doesn't matter which one you use. Now you can use the maximum entropy distribution to sample uniformly from the target set. But the problem is that this is an acceptance rejection method with a probability of accepting very small. So in practice, what you could use is the sequential algorithm instead. This algorithm always reaches the target set, but in exchange, you lose the uniformity of the samples. However, if you want to correct for non-uniformity, you can always use importance sampling. And when using the sequential algorithm, the order in which you sample the points is important, and that will affect the distribution of the importance sampling weights. But you can use adaptive orders, such as the most uniform order, and that will give you better results in practice. So yeah, that's the end of the talk. I want to thank you for listening to me. If you have any questions, please feel free to send me an email. And I hope you stay safe and healthy and that you enjoy the rest of the conference. Thank you again.